Okay, hello. Welcome back to your module 1. Okay, so we are still on your simple stress. So in your unit 1, we discussed about normal stress, or that is axial stress. Okay, it could be because of a tension or tensile force that is applied on an area perpendicular to that force, or it could be a tension force that is applied on an area that is again perpendicular to that force. So okay, you can say that that is normal once the area and the force are perpendicular with each other. So that is your unit 1. Now let's proceed with your unit 2. So okay, again, this is defined in your this is your shear stress. Okay, this is defined in your introduction, wherein it is the stress experienced by an area which is parallel to the force being resisted. Okay, so in this unit, so this is our unit learning outcome. First is to differentiate what is normal and then shear stress. Okay, let's try to differentiate these two, because these are the two types of stresses that commonly goes together with each other. Okay, and then compute for shear stress. Okay, so that is our after in this unit 2 of module 1. So again, let's try to elaborate further the definition of shear stress, that is area or force parallel to area. That is the common definition of shear stress. Let's try to elaborate that one. Okay, so force is parallel to the area resisting the force causing shear stress. Okay, it differs to normal. If we say normal, again, that could be a tensile or compressive. Okay, that could be because of tensile force or compression force. So it differs to normal stresses, okay, which are caused by forces perpendicular to the area on which they act. Shearing stress is also known as tangential stress. Okay, we call the normal as axial because the line of action of the P is with the axis of the member. So if you will cut the member, the area is perpendicular to the force. If this is the member, the same axis, the force is the same axis with the member. Now, why do we call this one tangential? Okay, tangential because tangent, if we say tangent, that is passing on a certain point, okay, at a 90 degrees. So again, if this is the area, the force is passing at an or tangent to this area at a 90 degrees, or we call this one tangent because it is intersecting or touching that area at a 90 degrees. Okay, so this is the force. It will try to pass that one at a 90 degree, not 90 degrees, definitely. I mean, for you not to be confused with the 90 degrees, I mean, is the tangent because they are parallel. Okay, tangential. So how will this resist? In your normal or axial, it will resist because of it's either trying to stop the force, or it is trying from pushing, or trying to stop the force from pulling. Okay, that is normal. Okay, it's either pushing or pulling. That is normal stress. Tangential is actually parallel. So this is the force, this is the area, parallel. Okay, parallel. So how will that area resist this force so that you will have a stress? Because again, due to resisting the applied load or force, that is where we will be having what we call as stress. Okay, so let's say this is the resisting area and this is the force parallel. How will this resist? Okay, that will resist through what we call as in physics as friction. Okay, the resistance of the area and the force is friction. Okay, friction. The friction will try to stop the force. Okay, that is when we will be having, and that is stress. Due to that friction that is trying to resist the force parallel to that area is what we call as the shear stress. Okay, therefore we just simply call this one as an stress, which is a product or an stress due to a force resisted by an area parallel, or parallel area with a force is shear stress. Okay, but you should put that in your mind, that how will that resist? How will the shear stress resist a force? Is through friction. Okay, friction of the surface. That's why parallel area and a force is a shear stress. Okay, so this is our formula for that. In normal, we call that one sigma. Okay, in shear stress, we call that one the tau. Okay, it is another Greek letter, tau. which is representing shear stress. Wherein your V there is still a force, but let's actually any force will do. The P in your normal can be any force as long as that is perpendicular. This V here is also any force as long as that is parallel to the resisting area. But just for us to be differentiating the formula, let's call it as shearing force V. Okay, shearing force V. But that could be any force. Sorry. Again, so the type of stress depends on the orientation of the resisting area. If that is perpendicular, it is an axial or normal. If it is parallel, it will be shear. So area is the cross-section area parallel to the force B. Okay. So again, these are just the reminder here. And let's have an example, okay, to better understand your shear stress. So what force is required to punch a 20 millimeter diameter hole in a plate that is 25 mm thick? Okay, the plate shear strength is 350 meganewton per meter squared. This is meter squared. Okay, that should be a power. Okay, so what does this mean? Okay, so look at the figure. So originally we have this as a solid plate, okay, and this circular here is a puncher. It is a puncher that will create a hole. Okay, that is a puncher. So we are going to make use of this cylindrical shape puncher to create the same size of course, the same size of hole within your solid plate. So after the punching, then that separates this part of the plate. Then you punch a hole with the same size as your puncher. Okay, so the question there is what force? Okay, so in our figure that is force P. So that is what I'm saying. It could be represented V in our formula, but it could be any force. Okay, as long as that force is parallel to the resisting area. So okay, so look at the scenario here. We will try to punch a hole. So what will resist? What will resist? Definitely, this is not a. We are not referring to a normal stress, because if we will just try to focus on the puncher without the plate, you are looking at a P perpendicular to the area of the puncher. Okay, this is the puncher, area of the puncher. This is the P. That is a normal stress. If that is, if you are just focusing on the puncher alone. But since we are focusing on the scenario of the plate and the puncher that will try to create a hole, then let's try to analyze that. There is a shear there. Okay. So originally there is no hole here. Okay, you are going to punch that one. So what will resist? What will resist that force P in creating such circular hole in your plate? What will resist is, of course, okay, imagine this as your plate. You will try to punch a hole. Okay, you will try to punch a hole within. So what will resist the punching force? What will resist is the thickness. Okay. For example, this is very, very thin. It is easier for you to just punch a hole on that plate. But once that will be thicker, or it depends on the strength of this steel, once this will be thicker, then it will be harder for you. So what will resist is the thickness. Okay, the thickness of the plate. The thickness of the plate. That will resist the punching force. But the question there, yes, the thickness, but we are referring to an stress. So we should have an area. So let's say this is the circular. Okay, circular. What is the area that will resist? Okay, so if you try to look at our figure here, what will resist? What is the area that will resist that one? Is this area shaded? Okay, look at this. In the hole, that is the shaded area. This is a circular shape. Or in the removed part, that is same as that. So that is the area that will resist. So what will happen? How will this area resist this P? Is because of the shearing. Okay. Okay. Just imagine this circular part that will be removed. Okay. Imagine that one that will be removed from the plate. Let's say this is the plate. This is the circular part that will be punched. So how will that be removed? Okay. This way. Imagine that one. So this part of the hole that is removed and the remaining part of the plate, the resisting will be the friction. Okay, the resisting reaction, there will be the friction between the remaining and the punched hole within the area. Okay, so that is the resisting force that will try to resist your punching force P. So that is where you will have there a shear stress. The shear stress is experienced by that area, okay, where the hole is being punched. So that's it. That is what is presented in the figure. Okay. So the question there, what is given? Okay, let's write down the given so that you will know what is unknown. Okay, so what force is required? So definitely your unknown is P. To punch at 20 mm diameter, so that is the diameter of the hole. So let's say that is D, and then in a plate that is 25 mm thick, so let's say that is T, thickness. But we have there a tau, that is your tau, that is shear stress, that is the strength, shear strength. Okay. Maybe you are confused with stress and strength. Okay. If you are referring to the capacity of a material, that is stress, we call that one the strength. But if you are just referring to the effect of the force on the area, that is the stress. Okay, that is the stress that we are talking about. But if you are referring to the amount of that stress that can be carried by that type of material, that is the strength. Okay. So if we are referring to how much normal stress it will carry, that is the normal or actual strength. If we are talking about how much shear stress that material can carry, we call that one the shear strength or tangential strength. Okay, so that you will differentiate what is, when do we call this one strength and when do we call this one stress. So in here, it says there that the plate shear strength, so it means strength, that is the strength, that is how much shear stress the plate can carry. Okay, because of the type of material the plate is composed with. So that is the shear stress, the amount of shear stress that the plate can carry, which is 350 meganewton per meter squared, or this is again megapascal. Okay, so again what we are trying to find is force, punching force P. Now, okay, we are just playing with the formula of shear stress. Tau is equal to V over A. V is the force, A is the parallel area. So again, by the way, how did we figure out that that is the area? Because, how did we figure out that this is shear? I mean, because the area resisting the force is parallel. Okay, look at the area. Okay, this is the area. Let's say this is the area. The area is parallel to the direction of the force. Okay, say this is the force. Parallel, okay, parallel. So that is a shear stress. Okay. However, in this formula, let's say that your shearing force B is your P, since that is the one that will cause the scenario. Okay. So area there is, what is the area again? Okay, let's try to figure out. The area there is the shaded. So what is that area? That is the question. If you will try to spread the area, okay, try to cut this circular area. Cut this one and then try to spread that one. That is just originally, let's say that is curved. Cut that one and then spread. That will be just a slant. Flat, rectangular. So that is this figure here, this rectangular figure here. Okay. So if you try to return this back, this end to that other end in a circular manner, then that will form again the circular area here. Okay, that is how we ended up with this area. So again, because we need that area for the A in your formula. So therefore, if that is the simplification of the area, then what is the area? That is just a simple rectangle, isn't it? What is the dimension of the rectangle? The thickness of that will be the same as the thickness of your rectangle. But the question, what is the length of that? The length of that is, again, if you will try to recall, if I will try to put this back on that other end in a circular manner, what will be this side? That is the circle itself, isn't it? That will be the circle itself. So that is, what is that circle itself? The length of the circle itself, that is the circumference. So what do we have? Is the dimension is the diameter. What dimension do we have? Is the diameter. So circumference is pi d. But if you have the dimension as the radius, that is 2 pi r, isn't it? Circumference. Therefore, the length of this rectangle, simplified area rectangle, is the circumference of the circle, which is pi d times that thickness. So the area is pi d times t. Okay, so pi, what is the 20? That is the diameter. What is the t? That is the thickness. So mm will be mm squared. Okay, so that is our area. That's our area. Okay, so again, what are we trying to find is the P. So P is equal to tau, since we are given tau, and then we figure out what is area. Then all we need to do is solve for the force P. Okay, so by the way, it's up to you how you will compute this one. This is just directly transformed to kilonewton. But this is, okay, what I did here is that 350, that is megapascal, okay, which is meganewton per mm squared, per meter squared, okay, per meter squared. And then I will convert that one to newton. So by multiplying your mega, that is mega is 10 raised to 6, okay, that's why there is no mega here. So newton per meter squared. However, if that is the case, then since actually what I need is not the area, so I do not need to put that in mm, okay. Since the area will cancel out, what I need is the force. So it could be in newton or kilonewton. But the question here is, if I use that newton as meter squared, you need to put that area into meter squared. So transform that one by dividing by 1000 squared. Again, that is just a simple. That is just a simple what to call this one, unit conversion. Okay, so this is the area in millimeter squared. So for us to make that meter squared, divide it by 1000 squared, since 1 meter is 1000 mm squared, that one. Okay, so compute that one. That will be 5498 something, that is newton, but I divide it by 1000 to make it kilonewton, since most of the units, if that is a 1000 newton, that is better expressed in kilonewton. So okay, so let's try to check again. 350 times 10 raised to 6 times 20 times 25 pi over 1000 squared. So we have here 549,778.71 newton. That is your answer supposedly, but I directly divide it by 1000 so that I will make it as kilonewton. So that is 54978, or I rounded it to first decimal. Okay, it's up to you. Depends on the requirement. Okay, depends on the requirement of the problem. So you can put this in kilonewton or newton. Okay, the point here is that as long as you know how to manipulate the equation itself. Okay, so that is your number one. Therefore, what does that mean? That in order for us to be able to punch that size of a hole on the plate, which is 25 mm thick, you need to have at least, okay, at least, that is the least amount of P or force that you will apply for you to be able to punch that size of hole on that certain thickness of plate. But of course, once you will increase that one, that will be easier for you to punch. The higher the P, the easier for you to punch. But once that is lower than 549.8 kilonewton, then you will not be able to punch that one because of the thickness. Okay, and that because of the strength of the plate. So that's it. That is our example number one. Let's have next example. Okay, so find the smallest diameter bolt that can be used in the clips shown in figure 1 blah blah blah, or this is the figure. If P is equal to 400 kilonewton, okay, the shearing strength of the bolt is 300 megapascal. Okay, so let's try to understand this one. Let's try to understand the scenario of the problem. So we have here these clips. Okay, that clips is just the connection, okay, of the bolt and the what do you call this one, socket. Okay, socket. So the question there is, if you will try to apply a force P in this part of the socket, that will also be the same force that will be experienced on this side, because again, equilibrium. Okay, so this force P is trying now to destroy this connection, but that connection is being retained because of the bolt. So the stress is actually carried by the bolt. Okay, that is carried by this bolt here. Now the question, why is it that is under shear? Let's try to analyze. Why is it not normal? So what we are trying to figure out here is the bolt, guys. Okay, the bolt. maybe there is no problem with the tension of these members, okay, these two members connected, because if that is what you are trying to figure out, then that is a normal. So since the area of this member or that member is perpendicular to the force P, that is a normal, if that is what you are trying to understand. But what we are trying to understand here is the connection. So what we'll try to retain the connection for that not to break is the bolt. So the stress is handled by the bolt. So what type of stress is being handled by the bolt? That is the question. Okay. So this is the, just imagine this one. Okay. So let's say this is the member where the force is applied. This is the bolt. Okay. I will try to pull that one. This is fixed. Let's say this is fixed because it is countered by the other side. It is connected on the other side of the member. Okay, what will resist that one? Okay, what will resist this is the area of the bolt, isn't it? For that not to break, it is being resisted by the area of the bolt. Okay, so the question there, okay, if you try to look in our solution, we have here 2. Okay, in our solution again, what we're trying to figure out here is the smallest diameter. So what we are trying to figure out is the diameter of this bolt that will hold that force P. Given that force P is 400 kilonewton. Okay, what will that diameter that will be able to hold that force P? Okay, so we are referring here to the area. So playing with this equation, that will be our equation should be, okay, our equation here should be cross multiply that V divided by tau, but however I use this directly. Okay, so V is equal to tau times A. However, we will find out the unknown here, which is the part of the area. Okay, so it's up to you. You will just play this equation. Okay, so the question there is your V. Okay, that is the force P. That is the shearing force that will cause the shearing stress. So 400 kilonewtons, the tau, that is the strength of the bolt. Okay, that is the shearing strength of the bolt, and then that is 300 megapascals, I mean. So substitute. However, the area, that is what we do not know. The V and tau, we know that one. The area, that is where we do not know the diameter. So we can break this down, but the area, why is it multiplied to 2? That is my point here a while ago. Why is the area multiplied to 2? Okay. How many area will resist this one? Or let's imagine that this will break. So actually that is the figure here. This is the member where the P is applied. Let's imagine that that will break. So this will separate. This somewhere inside that member is the part of the bolt, and this is the remaining part of the bolt. So that will be separated. So how many area will be exposed due to the fracture? Is there are 2, 1 and 2. Okay, so again, that is the area on the top and the bottom. That is the one resisting. So there are 2 areas, and that is a single. The areas are the same since we are referring to a single bolt. Okay, single uniform diameter bolt. So that's why your area here is times 2. Okay, and what is the area of the circle again? Using the diameter, pi over 4 or 1/4 of pi diameter squared. So that is our area. Substitute to your formula. Okay, so I will transform that 400 into Newton, so multiply it by 10 raised to 3, and then your tau, okay, I will transform that one into Newton per meter squared instead of meganewton per meter squared. Okay, so okay, that's up to you. I did not show here in the solution the transformation of meter to millimeter, but in case I will just be ending up with the solution of this. Okay, look at this. This is Newton, so cancels. So meter squared will go on the other side. And then this is just a constant. The unknown is the diameter. Okay, the diameter. So once you will transfer this constant on the other side, that is meter squared, get the square root, so you will end up with a meter. But for that to become millimeter, you need to multiply it by 1000. So that is what I did here. But I just I did not show you. But again, that is just algebra. So it's up to you. Let's try to check again. We have here 400 times 10 raised to 3. Cross multiply 2 times 2. And below you will have 300 raised to times 10 raised to 6. Cross multiply is pi. times, again, get the square root of that, and then times 1000. Okay, that is in meter, and then times 1000. So 29.1346 or 29.13. So do not forget to multiply, since that is meter squared. So that again, as long as you know how to manipulate your unit, you should understand that you should make this one the same so that they will cancel out in case you want to end up with that certain type of unit. Okay, so again, it's up to you. This is just conversion. So the diameter, therefore, the diameter here is 29.13 millimeter. Okay, what does that mean? For us to handle, or for the joint not to break, you need to use a bolt with shearing strength of 3000 megapascal and a diameter of 29.13 at least, because you can use bigger than this, because the bigger the better. Okay, the bigger the stronger to carry the force, which is 400 kilonewtons. So this is the least, this is the smallest diameter that can carry that shear strength, or the shear stress, I mean. Okay, so that is number 2. Okay, let's go with number 3. Let's have one more. Okay, this problem is actually a combination of a normal and a shear stress. Okay, so that you can differentiate it further. Okay, not just by definition, but you can differentiate it in terms of the actual application. Okay, so as you can see in this formula here, this is just a reminder of the formulas. The one on top, reminder of the formulas that we need, okay, for the certain problem. So in this figure, a hole is to be punched out of the plate, having a shearing strength of 40 ksi. So we are now in English unit. Okay, so 40 ksi, or that is 4,000 for 40,000 pounds. Okay, pounds per square inch. That is the ksi. Okay, that is kips. Okay, kips. That is the kips. KSI is kips per square inch. Okay, PSI is pound per square inch. So that is the meaning of kips. I mean KSI and PSI. Kips is KSI is kips per square inch. PSI is pounds per square inch. Okay, so 1000 PSI is 1 KSI. Okay, so it means if you want to transform this one in pounds per square inch, that is 40,000. So the again, so let's go back. A hole is to be punched out of a plate with a shearing strength, so that is the strength of our plate, 40 KSI, and the compressive stress in the punch is limited punch, or that is the the puncher. Let's just try to change that one. Puncher. Let's just change that one to puncher, so that you will not be confused. Puncher. Oh. Okay. Okay. So we are trying to punch a plate with a strength of 40 ksi using a puncher with the compressive stress in the, okay, so that is the strength. Okay, that is the strength of the puncher, 50 ksi. So what does that mean? The strength of the steel, if ever this is steel, the strength of the steel used in the puncher is stronger than the strength of the steel used in the plate. We have different types of steel, so we have different types of we have different strength, okay, with respect to the type of steel. So the question there is, compute the maximum thickness of the plate in which a hole 2.5 inches in diameter can be punched. So that is our first problem. Second is that if the plate is 0.25 inch thick, determine the diameter of the smallest hole that can be punched. Okay, so let's try to understand this one. Let's try to focus on the first one. Okay, so what do we know? Let's focus on A. So what do we know here on A is the 40 ksi, the strength of the plate, and then the strength of the puncher. That is what we only know. Okay, but it says there, what is the compute the maximum thickness in the of the plate, which we can punch a 2.5 inch hole diameter. Okay, so what does that mean? The thickness of the plate varies. So that depends on how much. That depends on how much. Okay. How will I simplify this one? Okay, so what we are trying to find is the maximum thickness. Okay, that certain puncher can punch. Okay, to simplify the question. So the thickness depends on how much that puncher can punch. Okay, so first is let's try to establish how much can that puncher. Okay, how much is the strength of that puncher? So based on the puncher strength. Okay, so again, puncher, what is the type of stress on the puncher? Look at this. If I will cut the puncher, the area is perpendicular to P, so that is a normal force. Okay, or that's normal stress. So we are given the strength, which is the stress. Okay, strength. So that is how much stress the puncher can carry. So that is given. So playing around with this, all we need to find is how much P. Since actually we will be needing that P in your shearing later on, that force P in shearing later on. So we know that the stress the puncher can carry is the sigma, and the area is, since we are given, we are given a hole. We are given the diameter of hole that will be punched. Therefore, that diameter of the hole that will be punched is the same as the diameter of the puncher. Okay, so 2.5. So that is given here. So we can now figure out the area, and we are given the stress. Therefore, what we can find here is P, the force P. Okay. So, P is sigma A, and then your sigma is 50 ksi. Okay, 50 ksi. And then ksi again is kips per square inch. And then you will find the area in inch squared. Okay, so 1/4 pi diameter is 2.5 inches. That is the diameter of our puncher for us to create a 2.5 diameter hole. Okay, the puncher should be the same as the hole. And then that is the area. So I will multiply. This is the area is in inches squared, so that will cancel. You will end up with kips. So that is let's check again. 50 times 0.25, the 1/4, which is pi, times 2.5 squared. You will have here 625/8, or wait lang. Let's just check. Yeah, 625/8, or that is 78.125 pi. I will not multiply the pi, so that will be a whole number. But if you want to multiply, that is 245.43, 2.5.43, or 44, 47 or 44 kips. That is the value of P. That will be able to create that 2.5 inch. Okay, for us to maximize. Okay, again, we are focusing. We use the 50 kips here because we want to maximize the strength of the puncher. So that is how much P the puncher can carry. Okay, so that you will not be asking me why do we need to find the P? Okay, we need to find the P so that we will maximize how much P that puncher can carry. So that if we maximize the P that the puncher can carry, then that is the P. That is the maximum P that we will be using to punch a hole on the unknown thickness plate. So, okay, equivalent force, shear force of the plate. Let's go now on the plate. Okay, based on the plate, on the shear strength. Now on the plate that is a shear, just like example number 1, isn't it? On the puncher that is a normal, but in the plate that is a shear. So that is the equivalent shear strength of the plate. V is equal to, okay, how much force will punch that plate is V. Tau is the strength of the plate, and then area is the area of the hole to be punched. Okay, so V is the equivalent. That is the equivalent P. So I will be using the one with pi. That's the whole number. This is rounded, so I want to use the whole number. 78.125 pi kips. Okay, and then tau there is 40. We will try, of course, to maximize also. Okay, we want to use the entire strength of the plate. 40 kips per square inch, and then the area of the hole to be punched. Okay, where did we get this one again? Okay, guys, imagine the circle part. try to cut that one, spread that one, that is a rectangle, wherein the length of the rectangle is the circumference and the thickness is the same thickness. Okay, so this is the area. How did this happen? Again, pi d, that is the pi times d. Pi times 2.5 here, d is 2.5, that is the diameter. That is the circumference of the circle. And times the thickness, which is the unknown. Okay, thickness, which is the unknown. Now that is the only unknown, so play around with this. Okay, this skips, that skips, it will cancel. This is inch squared. Okay, this is inch squared, but that 2.5 is inch. Okay, remember that 2.5 is inch diameter. So inch squared, one of the inch will cancel, so the inch will go on the top on the other side, so that will end up as inch. So let's just try to check. Okay, 78.125 pi over 40 times 2.5 pi. So 25 over 32, or that is 0.78125, or to be rounded, 0.781 inch. So it means that for us to maximize, if we want to maximize the strength of the material used in the puncher, then we can punch up to 0.781 inch thick of that 40 KSI plate. Okay, so that is your first problem, A. Okay, we try to maximize the strength of the puncher, and that is the maximum thickness that it can punch. Okay, so once we go beyond this one, what will happen? There will be, the punching will not happen, because once we increase the force P, the plate will not be punched, because along the way, while we increase the force P, the puncher will fail. Okay, because we will now exceed the 50 KSI. So that is the only maximum thickness that we can punch, for us not to exceed the 50 KSI, because again, if we will try to exceed that one, that is the strength of the puncher, it will fail. The puncher will deform, or will be destroyed. Okay, let's proceed with the last. Okay, on the B. Okay, so if the plate is 0.25 inch thick, okay, so it is now fixed. The thickness is fixed. The plate is fixed. Determine the diameter of the smallest hole that can be produced, that can be punched. Okay. Now that is the question there. The thickness is fixed. The question there is the size of the hole that will be punched. So will that be affected? Okay, given the thickness, will that be affected? Will the hole size be affected? Yes, because the resisting area of the shear on the plate depends on the diameter of the hole. Okay, depends on the diameter of the hole, because the bigger the diameter of the hole, the bigger the area that will resist the shear. Okay, the bigger the area that will resist the shear. So the smaller, okay, if you'll try to look at the formula here, okay, the smaller the area, the bigger the stress. Okay, and we only limit ourselves to 40 KSI. Okay, the other way around, I mean, we should surpass that 40 KSI. So what we are trying to find the diameter of the smallest. Okay, that should be the smallest hole. Okay, so how will we do that? Based on the compression of the puncher. Okay, so again, let's try to focus first on the puncher, but that is, we are not going to maximize the strength of the puncher. Okay, that is not the point here. Okay, what we are trying to vary here is the size. Okay, so P is equal to sigma A. So the same sigma, we will use the 50 KSI. The area we do not know, since that is variable, since that is what we are trying to find. Okay, so the diameter, the area is in terms of diameter. So we will try to simplify this one. 50 times 1/4 is 12.5 pi d squared. I will not multiply for that to be whole number. Okay, so 12.5 d squared, and the unit of that is kips, since that is force P. So that is the equivalent shear force if I will transfer that one on the plate. So based on the shear strength of the plate, okay, so V there, or which is equal to P, is tau times A. Your tau here is 40. We are maximizing we are trying to, in your case number 2, in scenario number 2, we are maximizing plate, the strength of the plate and the strength of the puncher, we will try to equate this one so that they will fail at the same time. Okay, what should be the smallest hole that will be punched so that we will maximize the strength of the plate and the strength of the puncher? Okay, that is the B, unknown B. So equivalent is B is equal to P. Our P here is 12.5 pi d squared. Your B here is what? Okay, that depends again on the area. Your area is still unknown because of the diameter. So the area, okay, again, how is that? The area is the area of the area which will resist the friction. So that is again, I will cut that one that is to be spread on a rectangle, and the length of that rectangle is the circumference. Okay, times thickness. So this is your P. Okay, that is your P. On the other side is tau 40 times your area. Area is again circumference times thickness, since that is already given. So the unknown is still D. So we have here an unknown D on the from the puncher. We have an unknown D on the plate. So play around. This is now single variable. So D and D cancels. D and D cancel. One of the D cancels. So what will be left is 1D in here. So cross multiply that below, so that you will now divide. So pi and pi will definitely cancel as a whole. So that is the reason why I did not multiply. So you will end up here with 40 times 0.25 over 12.5. 4, that is 4 over 5, or that is 0.8 inch. Okay, so that is the D, the smallest D that we can punch to maximize the strength of the puncher and the steel. So it's okay for us to punch a bigger hole. Okay, it's okay for us to punch a bigger hole. It's okay. Okay, but once we go smaller than this diameter, we cannot do that because there will be failure on the puncher and the plate. Okay, again, why is it that there will be failure? There will be no a perfect hole that will be punched because these two will fail. Okay, that is the meaning of that. The puncher and the plate will fail. Maybe the plate will actually be crumpled. Okay, so there will be no hole that will be punched. Okay, and that is your combination of normal and shear stress. So again, so to differentiate a shear and the normal stresses, you need to understand how the area will resist. Will the area perpendicular be the one to resist the force? That is normal. Or will the area which is parallel be the one to resist the force? That is shear. So again, this is now critical thinking. This is now where your engineering mind should be working. Okay, this is now where we will be trying to sharpen your engineering skills. Okay, in your analysis, especially on each scenario of the situations. Okay, so let's review some concepts on shear. Okay, so shear stress. The force used in normal stress can also be considered as shear force. So again, the force will not determine the type of stress. The type of resistance, okay, how will the area resist? Is that area resisting by means of stop tension or compression? That is perpendicular, therefore that is normal or axial stress. Or will that area resist by friction? So the area should be parallel. So that is shear. So it says there in second concept is that the shear force is always parallel to the area under shear. And then double shear can occur if two sides of the body are experiencing shear. Actually, yes, that is in our example. Okay, so it depends. So again, for example, this is the bolt. Okay, there will be a lot of attachment. Let's say this one. This is a single member, and this is the bolt. There will be two attachments. So this one and the other one. So once that will be pulled, this will break. Okay, and there will be two areas that is resisting this part of the member. And then if this will break, yes, of course they should break at the same time. Okay, so there will be two areas here, and then there will be two areas due to this. So again, it depends on the scenario of the problem. Okay. So any question, we will you can comment that one below, or we will discuss this one on the live meeting. Okay, so thank you very much for watching.